Alright, here we have lecture 3.4, Characterizing Data, where we're going to discuss measures of center and variation. So two very important characteristics when studying any data set. Hey, what's the center or average value in a data set, and how varied is the data in the data set? So here we're going to introduce some terminology, notably the word distribution. So the distribution of a variable or data set refers to the way in which its values are spread over all possible values. So we kind of view data sets as distributions, and when studying a data distribution, we often wanted to try and determine, hey, what's the center of the data set? And there's two main ways we do that. Mean and median are kind of the two most common ways for describing the average or center of a data set. The mean is computed by adding up all the data values and dividing by the number of data values. So a lot of times this word mean is interchangeable with the word average. You'll probably hear me do that throughout the class and semester. So whenever I'm saying compute the average, I'm kind of referring to the mean. The median is the middle value in the sorted data set. So it's very important that you have the data set in ascending order. And what the median will do is it will partition the data set into two halves. And those two halves will have the same number of data values. So there's two ways the median can go. Either you're determining the median in a data set with an even number of data values or an odd number of data values. If there are an even number of data values, then the median will be in between two data values. If there are an odd number of data values, then the median will actually be that center data value. And then lastly, you got mode. Mode is the data value that occurs most frequently in a data set. So let's go ahead and practice this with some examples. So here we have some quiz scores, and they are already in order, which is good. Let's go ahead and see how many data values we have here. So we have, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 data values. So we'll start by computing the mean. So the mean is just going to be computed by adding up all the values, 3 plus 4 plus 6 plus dot, dot, dot. So you're going to add them all up, divide by 13. So I'm going to go ahead and do that now. And I get 7.23 approximately. So our mean data value, or our mean quiz score, is 7.23. Now, as for the median, let's go ahead and think about this. If we have 13 data values, then the best way we can split this is to have 6 in the lower half and 6 in the upper half. That means we're going to have one data value left over. That data value left over is actually going to be the median. So if I want to have 6 in the lower half, my median is going to be the 7th data value. So 1, 2, 3, 4, 5, 6. There's my median. Now, I know my median is correct if it breaks the data set into two equal size halves. So if I look at this median, I have 6 data values below it and 6 data values above it. So that indicates that we made the correct selection of our median. And then last is the mode. The mode is the most frequent data value, and in this case 7, because it occurs with a frequency of 3. So as you can see, if we have an odd number of data values, the median will be one of those data values. Let's look at a data set where we have an even number of data values. So if we look at example number 2, we have 16 data values. 16 data values. So let's go ahead and do the median first. The mean. Let's go ahead and do the mean first. So that's where you add them all up and divide by the number of data values. So we have 16. So let's go ahead and add all those up. And we get, let's see here, 73.31 approximately. So there's our mean test score. Now let's go ahead and do the median. So if I take 16 data values, I can do 8 in the lower half and 8 in the upper half. That will use up all the data values in the data set. So that means our median is going to actually be in between. So our median here is going to be in between the 8th and 9th data value. So it's basically in between 72 and 81. So if I want to compute the number in between two numbers, you actually take their mean. So add them together, divide by 2 to compute the number in between. And that will give us 76.5. So our median is 76.5. The idea is our median is right here. And it breaks it into two halves. So half the data values are below 76.5, half are above 76.5. So there's our mean, there's our median. As for the mode, what's the most frequent data value? I can see 72 occurs twice and 91 occurs twice. So it's a tie between those two data values. Alright, cool. So that's mean, median, and mode out of the way. So let's introduce the concept of outliers. An outlier in a data set is a data value that is much higher or much lower than almost all other data values. So it's way below all the other data values or way above the other data values. So let's go ahead and look at an example here. So a coach is tracking the heart rates of 5 athletes during a workout, and he records the following readings from the heart rate sensors. So the heart rate sensors tell him one athlete had an average heart rate of 130, another said 135, another said 145, the fourth said 140, the fifth said 325. So if I want to compute the mean, add them all up, divide accordingly. So there's 5 data values here. So the mean of this data set is 175, whereas the median, here we have an odd number of data values, so our median will be the center data value, which in this case is 145. Notice the median breaks it into two halves with 2 below and 2 above. The question is the mean or median a better measure of what the average heart rate is during the workout? Well, definitely the median is better. That's because you have a crazy outlier, right? That 325 is some crazy outlier. It's probably a malfunctioning sensor is what it is. And with a data set this small, an outlier is going to play havoc with the mean. So outliers can impact the mean, particularly in small data sets. So in this case, if we want to try and describe the average or center heart rate for these 5 athletes, the median is much better. Much better. So that's how we can determine center of a data set. We also want to be able to describe or measure the variation in a data set. So variation describes how widely data values are spread out about the center. So if we were to look at kind of 3 bell curve or 3 kind of normal distributions here, we can see an example of low variation, moderate variation, and high variation. You can see with the low variation, all my data values are kind of clumped in between these two values. Whereas with moderate variation, the net widens. In high variation, data values are spread out even more. So you can see with low variation, very small spread. High variation, we have a much larger spread of data values. So let's look at this example here. Which do you expect to have higher variation? Marathon run times from the Savannah Rock and Roll Marathon or marathon run times from the Olympic Marathon? Which one do you expect to be more varied? Well, it's definitely going to be the Savannah Rock and Roll Marathon. That's going to have much higher variation because if you think about it, you're going to have some very, very high-level athletes running in the Savannah Rock and Roll Marathon, but you're also going to have some not so high-level athletes, some people just walking most of the marathon, and a lot of people in between. So you're going to have a very diverse set of people running in the rock and roll marathons, which is going to give you a very varied set of run times. Whereas if you look at the Olympic marathon, everybody in the Olympic marathon is a world-class athlete. So those times are going to be much closer together, and there's going to be far less variation in those times than in the Savannah marathon. So the Savannah is definitely going to be more varied. Now this begs the question, is there a way we can measure how varied a data set is? I kind of described why we expect the Savannah marathon to be more varied than the Olympic marathon, but can you prove it with some numerical measure? Well, one way of looking at it is saying, well, compare the lowest time to the highest time. Suppose I have two sets of test scores. In one set of test scores, the lowest was an 88 and the highest was a 100. So all the scores are in between 88 and 100. Whereas in another section, the lowest score was a 17 and the highest was a 100. So therefore, all the scores are in between 17 and 100. So that's a larger potential spread there. So that's essentially looking at the range. So the range of a data set is the difference between the lowest and the highest data value. We basically just take the highest minus the lowest. And it shows us how wide the interval in which the data values exist is. So let's go ahead and look at an example. Let's see if range is a good way of measuring variation in a data set. So here we got two sets of quiz scores. You see below. Compute the range of each. So let's compute that quiz 1 range. So the highest was a 10, the lowest was a 1, so the range is a 9. And let's compute the quiz 2 range. So if we look at quiz 2, the highest score was a 10, the lowest score was a 6, I believe. Yep, was a 6, so there the range is 4. So if we look at the two ranges, the quiz 1 has greater range. Does that mean quiz 1 has more variation? Well, go ahead and look at those quiz scores. Which one looks more varied to you? Definitely quiz 2. If you look at quiz 1, every student got a 10 except for one student who got a 1. Whereas if you look at the scores for quiz 2, they're all over the board. We got some got 10s, got 1 6, couple of 7s, an 8, couple of 9s. Much more variation in the data. So we have a problem here. The range is not a good measurement of how varied a data set is. That's because we have an outlier in quiz 1. And what outliers do to the range is they greatly increase the range. So that's what happens when you have an outlier. It's going to blow your range up. It's going to make it significantly larger. That's because the range only looks at two data values. When you're computing range, you're only looking at the highest data value and the lowest data value. That's it. You're ignoring all the data values in between. Now, that doesn't mean range is useless, right? We can see here, if you have a small range, that does guarantee low variation, right? If you got a small range, then all the data values must be in between those lowest and highest. And if those lowest and highest are pretty close together, then all your data values have to be close together. But a large range is rather inconclusive. A large range does not necessarily mean high variation. Just look at that last example. You could just have a single outlier blowing it up. So the problem with the range is we're only looking at two data values. So we need to bump those numbers up. We need to look at more than just the lowest and the highest, which brings us to a 5-number summary. So here we're going to look at 5 numbers from a data set, or with respect to a data set. Those 5 numbers in the 5-number summary are the lowest value, the lower quartile, which is the median of the lower half, the median itself, the upper quartile, which is the median of the upper half, and the highest value. And you can use these 5 numbers in the 5-number summary to construct a box plot. You may also know this as a box and whisker plot. So different texts will give it a different name, but box plot and box and whisker plots are referring to the same type of graph. And the way it works basically is your lower quartile, median, upper quartile make up the box in the box plot, whereas the highest, and lowest values make up your whiskers. So let's demonstrate this with an example. So looking at this example, provide a 5-number summary and a box plot for the given data set. Well, first things first, if we're computing medians, which is what a 5-number summary is all about, it's median of the data set, median of the lower half, median of the upper half. That's your 5-number summary. If we're computing a bunch of medians, we do have to put that data set in order. So let's go ahead and put this data set in order. The lowest number I'm seeing is 33. Cross that out, and then we've got, what's the next one? 51. And then the next lowest is anything in the 60s. I'm not seeing anything in the 60s. I got 73 is the next lowest. And then 76 and 77. 76 and 77. And then the next lowest I'm seeing is an 82 and 85 and 90, 92, 100. Alright, cool. So now we have it in order. So we got our lowest, our lower quartile, our median, our upper quartile, and the highest. So I'll just kind of label them as follows. The lowest and the highest are self-explanatory. It's 33 and 100 are the lowest and highest data values. Now I can't figure out the quartiles until I get the median first. So let's see how many data values we have here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 data values. So if I have 10 data values and I want to break that in half, I'll have 5 in the lower half, 5 in the upper half. So 1, 2, 3, 4, 5. Right there. There's my median partitioning it. So I need to figure out the number in between 77 and 72. So I add them together, divide by 2. Basically compute the mean of those two center values. And that will be 79.5. So my median is 79.5. Now I'm going to compute the lower quartile and the upper quartile. So the lower quartile is going to be the median in the lower half. So in the lower half I have 5 data values. So if I have 5 data values and I want to break it in half, the best I can do is having 2 in the lower half, 2 in the upper half. So to break that up, that would be a 73. That'll break it into, break that lower half in half. And then in the upper half, we also have 5 data values. If we want to break that in half, I would refer to 90. So basically, what we're doing with a 5-number summary is breaking the data set into quarters. Right? We have 4 quarters here, and all of them have the same number of data values. I have 2 data values in the first quarter, 2 data values in the second quarter, 2 data values in the third quarter, 2 data values in the fourth quarter. So let's go ahead and make a box plot here. So our range basically goes from 33 to 100. So I'll just start at 30, go in increments of 5. So 50, 60. Every hash mark is 5 units. 90. Rounding out of room here. 100. Okay. And then we just plot our 5 numbers above the corresponding value. So 33 is going to fall right around there. 73 is going to fall right here. 79.5 is right there. 90 is right there. And 100. So the whiskers connect your outer values. And then the box is constructed on the lower quartile, upper quartile, and the median, and we draw a line through the median. So that's what your box plot looks like. You can kind of see why this is called a box and whisker plot. And it kind of just shows you the range of all the different quarters. So you can see a very long whisker on the left. That's an indicator of an outlier. So a long whisker is an indicator of an outlier typically. But not always. This is a good sign of it. And there we see our lower quartile, our median, our upper quartile. So there's our box plot. Nice little visual representation of the data set. So we can see we have a wider range in our third quarter than in our second quarter. But I digress. So that's a 5-number summary, can be used to construct a box plot. Now, shouldn't we consider every data value when measuring the variation? Right here, we're just partitioning the data set into 4 sections, essentially. But don't we want to look at every data value? Well, yes. And if we want to look at every data value when computing or measuring variation, the gold standard is what we call standard deviation. So we use standard deviation to measure how spread out data values are. And there's 2 types of standard deviation: population standard deviation, given by that letter sigma, and sample standard deviation, which is always represented by the letter S. So the idea with standard deviation is we compute each data value's distance from the center, or mean, square it, average it essentially, and then take the square root. So it's kind of a way of measuring average distance from the center, so to speak. With some kind of modifications there. So please carefully read through that. The letter N always represents the number of data values. Sigma always represents the population standard deviation. X sub I represents the ith data value. So X sub 1 would be the first data value. X sub 7 would be the 7th data value, and so on. Mu is the population mean. S is sample standard deviation, and this X bar always represents sample mean. So here we have sample statistics versus population parameters. So X bar is the sample mean, and we use that to approximate the population mean. S is the sample standard deviation. We use that to approximate the population standard deviation. And our population variance is just the population standard deviation squared. Sample variance is sample standard deviation squared. And if you're taking a stats class, you want to become familiar with this notation and these letters. All right. Highly recommend you also read pages 263 through 266, which walk you through those formulas above and how to compute standard deviation. We'll go ahead and practice it with an example. So let's look at this example. We've got 2 different brands of AA batteries being tested, and their battery life is listed below from the following experiment. Let's go ahead and compute standard deviation. We're going to do it for each brand. So we got brand A versus brand B. Now, first thing we need to realize, hey, are we doing sample standard deviation or population standard deviation? Well, here we looked at 4 batteries from each brand. That's not every single battery that this brand produces. It's a sample. Therefore, we're going to use sample standard deviation. And sample standard deviation is going to be your default one. So make sure you're typically defaulting to sample standard deviation. So the first thing we need to do when computing standard deviation is compute the mean, what we represent by X bar. So let's look at brand A and compute the mean. So all we got to do is add them all up and divide by 4. So if we compute the mean there, we get 11.625. And then we're still going to take each data value, which I'll represent by dV. We're going to figure out how far it is from the mean. And then we're going to take that difference and square it. This is known as the squared deviation. So our data values are 12, 12.5, 11, and 11. So let's look at data value 12. How far is 12 from 11.625? When you subtract them, you get 0.375. How far is 12.5 from the average or mean? Well, subtract and you'll get 0.875. And then how far is 11? 11 slightly below, so when we subtract, we'll get a negative 0.625. And 11 minus 11.625 will give us negative 0.625. We then take each one of those values and square it. And when you square each one of those numbers, you'll get the following. last one. And then if you look back on the previous page at the formula, we take those squared deviations, add them all up. So when we take the sum, we get 1.6875. And then the sample standard deviation is a big giant square root. We take that sum and divide by the number of data values minus 1. So we have 4 data values here. So we'll divide by 3, essentially, and we get 0.75 approximately. So we had a standard deviation of basically 3/4 of an hour between the different batteries in this brand. Now let's look at brand B. It's going to be the same thing. First thing we want to do is compute the average. So add up all those data values and divide by 4, and we get an average battery life of 12. Alright, cool. And then we're going to do the same thing. We're going to compute our squared deviations. So we're going to take each data value, which is 10, 14, 15, 9. Compute how far it is from that data value to the average or mean, and then square that deviation. So how far is 10 from the average of 12? It's 2 below. 14 is 2 above. 15 is 3 above. 9 is 3 below. And then we're going to square each one of those. So negative 2 squared is 4. 2 squared is 4. 3 squared is 9. 3 squared is 9. Add them all together and you get 26. We're now almost done. Sample standard deviation is going to take that total and divide by the number of data values minus 1, which will get us approximately 2.94. So that means the standard deviation for this brand of batteries is close to 3 hours. That's significant. That means you have a lot of variation in that brand. So let's go to answer these remaining questions here. Which battery has a greater average battery life? So look at the two averages. The average for brand A is 11.6 hours. For brand B, it's 12 hours. So brand B has a slightly better average battery life. But which brand is more consistent? So which one has less variation? Well, if we look at the standard deviations, the standard deviation for brand A is 0.75, whereas for brand B, it's way larger at almost 3. So brand A is way more consistent. And just look at the data values. Right. All the battery lives for brand A, all the batteries lasted somewhere between 11 and 12 and a half hours. So they were all pretty close to right at 12 hours. Whereas in brand B, you had one battery last for 9 hours, another one lasted for 15 hours, one lasted for 10, and another 14. So those are kind of all over the map. So which brand do you think is better? So brand B technically has a better average battery life, slightly better average, but the quality control is way worse, because if you look at the consistency, they are far less consistent. You know, if you grab a brand B battery, maybe it lasts for 15 hours, maybe it lasts for 9. So yeah, it has a better average battery life, but it's far less consistent. So I would actually say brand A is the better brand. Yes, it has a slightly lower average, but at least those batteries are consistent, right? You know what you're getting when you buy brand A. Whereas brand B, who knows if you're going to get a bad battery or a good battery? You just don't know. They're far less consistent, which is typically an indicator of poor quality control in the production. But I digress. That is standard deviation. Please, I highly recommend you read that page 263 through 266 in the book. It does a fantastic job of walking you through the process of computing standard deviation. All right, keep up the hard work and have a wonderful day.